Another look and show a different perspective related to the specifically the sum of the squares and the sum of square errors, and talk about again where these come from. You probably saw these in the graph that we created on CodeApp, and it was the output from the GeoGebra. So I wanted to give you a little bit of algebra behind this. So again, I'm focusing on, remember, this is my response variable, and this is my explanatory. Then the score is my response. So again, I'm going to focus on taking the deviation from the mean. So that is in cell B6. And I want to use the mean on all 5 of these computations. So I'm going to go $D, $3, hit return, and drag this down. And now I'm going to take the sum of these just to show you something. It shouldn't surprise you, but it's a little bit of review from something we did earlier. But again, the sum of the deviations from the mean should equal 0. But I'm not interested in the sum of deviations from the mean. I'm looking for the sum of squares. So I'm going to take that column from column C, deviation mean. And what I'm going to do is I'm going to take each of those values and I'm going to square it. So that's in C6 caret squared. And I'm going to drag that down. Again, don't care about that anymore, what that is. But again, you should have seen that number pop up. But if I take the sum of these, D6 to D10, that number should look familiar to you. That's the SYY. So deviation from the mean, we square those, take the summation of those, we get to 392.8. Now, SSE is a little bit different because now we're bringing in the idea of the explanatory variable, and it's related to again, I'm going to bring this over here. Because again, it's related to our observed minus our expected values related to our line of best fit. And just for the sake of speeding this process up a little bit, I put our values for our line of best fit up here. So we've got, these are essentially our observed score. That's what happened. And now we're going to look at our predicted score. And we're going to use our line of best fit to figure out what those values are. And I'm going to need to use the number of hours to put those in. So again, watch very carefully what I do. I'm going to take equals, and I know my slope, so that is in D1. So I'm going to go put that, and I'm going to fix that D1. And I'm going to multiply that by the value of my explanatory variable. That happens to be an A6. So I'm just going to type in A6 because I want it to roll through as I go down. I want to go A6, A7, A8, A9, A10, A11. And then I'm going to add on my y-intercept, which in this case is in cell D2. So $D, $2, because I want to fix that. And I'm going to hit return. And I'm going to drag that all the way down. Okay, and those are predicted values. So based on our least square model or linear regression model, those are the values we should get. What I'm going to do now is I'm going to do similar. I'm going to take a deviation, but in this particular case, we call these specifically the residual, if I can spell it right. And so there we go. We're going to take our residual, and I'm going to take the observed minus predicted. So that's going to be F6 minus G6. And I'm going to drag that down. And again, similar to what we did earlier, sum of residuals, I bet. Let's just see if this happens, how close. Sometimes due to rounding errors, we don't get this exactly, but we're going to check it out and see. H6 to H10. Yeah, so we're pretty close to 0. So the idea, the sum of the deviations from the mean, we're dealing with one variable, bivariate or a univariate data is equal to 0, which we got over here. And now over here, we got something close to 0 again due to rounding, but the sum of the residuals should equal 0 as well. And so that deals with bivariate data, and you can kind of see that happen. I'm going to leave that sum there though, because I want to show you something in the process of doing this. So H6 to H10 again, I want to leave that there. So show you that, and then I'm going to take the residual squared, similar to what I did earlier. So I'm going to get equals, let's see, H6, square that, scroll down here, and I'm going to take the sum. And again, when you do this, you can play around with this a little bit, but we're going to go I6 to I10. That's our values, and again, you should see a value very similar to that. That's our SSE here. So again, I'll make that red. Make that red so we can see that. And then here's our SYY. Make that green. Make that green so we can see it. Make it visible. So anyway, so we've got these two values, and this is the sum of square deviation from the mean. And again, I'll show you that in a minute. I think if I can just scroll down and show this, I think it's right down here. So when we did this with respect to sum of squares, those were the area of those squares. Again, that was 393 here. And then think about when it went down to here. It doesn't show the reduction here, but we can kind of see using that same line. Again, we've got a smaller sum of squares, and you can see that in the computations that are going on here. So last but not least, I want to show you how R squared is computed. Again, one thing I want to point out is if you play around with the slope, these values, again, the way we set them up, you'll see that the residuals will not equal 0, and you'll get larger numbers here. Again, this is called the least square regression line because this is the least sum of squares that we can create. You can punch different numbers in for the slope and y-intercept and see that you'll get bigger values, but that's why we call it a least square regression line. So just to finish, to compute R squared, which is called the coefficient of determination, we want to know what percentage of the variation in the response variable. In this particular case, our response variable is a score. So what percentage of that variation did we remove or explain by using the explanatory variable in considering the sum of squares? So again, we take that difference. We can see that it was at one point, it was in D11. So we've got D11 minus, what's that value that's in I11? And we're going to divide it by the total that we had before, which again was D11. That's how much we removed, that subtraction. And so we divide by D11, and you get a value again that should be fairly close to, again, I just want to illustrate this, should be right next to that value right here. It should be about the same. Maybe a little rounding, a little bit off, but you get the idea. So again, those are the differences. Again, univariate data, one variable. We're focusing on just the response variable here. Think about these computations. All we worried about was the mean of the response in this case, and the sum of the deviations from the mean were equal to 0. We square those, we get that value. That's SYY. And then over here, now we're dealing with the line of best fit. We're thinking of predicting that score based on the slope and y-intercept of that line. Computed residuals. Sum of the residuals, again, should be equal to 0. And then we square those residuals, and that's the value that we get. That's SSE. It's right here. And we find out how much error we removed. That's the value here. That corresponds with R squared. That's the coefficient of determination. So again, in this particular case, the number of hours explained 93% of the variation that we were seeing in scores. So it seems to be an effective model for predicting, or at least reducing the error in the sum of squares that we're seeing. So again, just wanted to give you an overview of that and give you a connection between what you were seeing in the GeoGebra output, what you were seeing graphically in the code app.